Welcome to the Explainer. Ever stop and think about the last video you streamed? It probably showed up on your screen perfectly, right? But how did it do that? See, between you and that video, there's this invisible conversation happening, a constant back and forth. Today, we're pulling back the curtain on the fundamental rules of that conversation, the rules of data link control that literally stop our digital world from collapsing into total chaos. So let's start with the most basic problem of all in digital communication. How does a computer know where one message ends and the next one begins? Well, this quote right here gives us the perfect analogy, and we're going to stick with it for this whole explainer. It all comes down to the good old envelope. You can't just send a letter, right? You have to put it in something first. Turns out computers have to do the exact same thing with data. So here's our game plan. First, we're going to build that digital envelope. Then, we'll figure out how to stop a massive data traffic jam. We'll kick things off in a perfect world where the mail never, ever gets lost. And then, we'll dive into the messy reality of handling errors. We'll watch as our delivery systems get smarter and smarter. And finally, we'll see why all this is the hidden foundation of pretty much everything you do online. All right, let's get into it. Part 1, the digital envelope. We're going to solve that first big problem. How do we stop all our data from just blurring into one long, useless stream of ones and zeros? The technical, kind of fancy term for creating this digital envelope is framing, and it's really just the process of taking raw data and packing it into these neat little bundles called frames so the computer on the other end can actually tell them apart. Let's bring it back to our mail analogy. Framing is literally the act of creating those digital envelopes. I mean, without them, the receiving computer would have zero idea where one piece of information ends and the next one starts. It would just be total, absolute chaos. And you know, there are basically two ways to go about this. You could make every single envelope the exact same size. That's super simple, but it's not very efficient. Or you could use variable-sized framing, which is way more flexible. But this creates a brand new headache. If every envelope is a different size, how in the world do you know where one ends and the next one begins? And a solution for this is honestly so clever. It's called byte stuffing. You decide on a special flag character that marks the end of the frame. But wait, what if that exact same character shows up in your actual data by pure chance? The system would get confused and cut your message short. So here's the trick. When the system sees that flag character inside the data, it stuffs a special escape character right before it. The receiver on the other end sees that escape character and knows, okay, the next character isn't a flag, it's just regular data. Then it just plucks the escape character out. It is such an elegant fix. Bit stuffing takes that exact same idea but brings it down to an even more basic level. Instead of a special character, the flag is a specific pattern of bits. So the sender is just constantly scanning the data stream. Anytime it spots 5 ones in a row, it automatically, bam, stuffs a 0 right after them. This just makes sure that the flag pattern is never created by accident. The receiver then does the opposite. It looks for that 5 ones, then a 0 pattern, and just pulls out the 0 to get the original data back. Same concept, just with individual bits. Okay, so we've neatly packaged all of our data into these perfect little envelopes. We're done, right? Well, not so fast. Now we have a totally new problem. How fast can we send them? If we send them way too fast, we're just going to overwhelm the receiver. And that brings us to part 2, managing the data flood. And the technical term for this is flow control. It's basically a set of rules with one simple goal: to stop a really fast sender from completely drowning a slower receiver in data. Let's go back to our postal worker. Imagine them just trying to cram more and more letters into a mailbox that's already overflowing. What happens? The letters just fall out onto the ground and get lost. That's exactly what happens with data. Flow control is basically the mailbox itself, being able to yell back to the sender, "Hey, I'm full. Give me a second to catch up here." So, to really understand how flow control works, let's step into a perfect world for a minute. Let's imagine a communication channel where data is never lost, never corrupted, a totally noiseless channel. Now, in this fantasy land, we could use what's called the simplest protocol. The sender just assumes the receiver is infinitely fast and just blasts data nonstop. But a more realistic approach, even in a perfect world, is stop and wait. With this one, the sender sends one frame, one letter, and then it literally stops and waits. It will not send the next letter until it gets an acknowledgement or an ACK back from the receiver. Think of it like a delivery-confirmed receipt. Once that ACK comes in, it sends the next one. It's super reliable, but you can probably see the big problem. All that waiting around is incredibly slow and inefficient. And that right there brings us to the most important question.
This perfect world is great for learning the basics, but it doesn't actually exist. The real internet is a noisy, chaotic, messy place. What happens when our digital mail gets lost in transit or shows up all garbled?
This is where we need something called error control. These are the protocols that were built for the real world, a world where you are guaranteed that things are gonna go wrong. And the main family of protocols that handles all this mess are known as automatic repeat request, or ARQ for short. These are the truly brilliant delivery systems that can spot and fix errors all by themselves.
So the first step in this evolution is stop and wait ARQ. It takes our simple stop and wait and gives it two crucial upgrades. First, a timer. When the sender sends a frame, it starts a stopwatch. If the delivery confirmed receipt doesn't get back in time, the sender just assumes the letter got lost and sends it again. Simple. Second, it adds sequence numbers. Imagine numbering your letters 0, then 1, then 0, then 1 again. This way, if the sender has to resend letter 0, the receiver gets it and knows, hey, I've already seen this one, and can just toss the duplicate.
But that one-at-a-time thing is still a major bottleneck. So the next step up is go back in, ARQ. The big idea here is, why send just one? Let's send a whole batch of letters at once. This is called a sliding window. But here's the catch, and it is a big one. Let's say letter number 2 gets lost, but 3, 4, and 5 all arrive just fine. Well, the receiver just throws them all out. It sends a message back saying, hey, I'm missing number 2, and the sender has to go all the way back and resend 2, 3, 4, and 5 all over again. It's definitely faster than one at a time, but it can be super wasteful. And that wastefulness leads us directly to the smartest protocol of the bunch, selective repeat ARQ. The idea here is so simple and powerful. Why are we resending letters that arrived perfectly fine? With this protocol, the receiver is much more intelligent. If letter 2 is lost, but 3, 4, and 5 show up, it holds on to them and just asks the sender, hey, can you just resend the one missing letter, number 2? This is by far the most efficient way to do things, but it does require a lot more complexity on both ends to keep track of what's what. And this table right here sums it all up perfectly. You've got stop and wait ARQ, simple, sends and receives one frame at a time. Then there's go back in ARQ. It's more efficient because it sends multiple frames, but it has to resend the entire batch if just one gets lost. And finally, selective repeat ARQ, the most efficient of all, with a smart receiver that can pinpoint exactly which frame needs to be resent, which saves a massive amount of time and bandwidth. And that brings us to our final section, the unseen backbone. Okay, we've gone through a lot of rules and procedures, but why are they still so incredibly important to everything we do online? Because what we've really been watching is an evolution of problem solving. We started with the simplest idea possible, a digital envelope or framing. Then we added a traffic cop to manage the speed. That's flow control. And then we built these incredibly smart postal workers that can automatically fix delivery mistakes. That's error control. These layers of logic built one on top of the other are the reason why when you click on a link, it just works. And that leaves us with one final, kind of mind-bending thought. These core ideas, framing, flow control, error correction, they were all figured out decades ago in a completely different era of technology. Yet, they are still the absolute bedrock of our modern network. So the question is, how do these ancient rules manage to adapt and scale to handle the insane demands of today's world, a world of 8K video streaming, global online gaming, and constant messaging? It really makes you think.